Alright everyone, today we have an A1707 that does not turn on after a liquid spill. So the primary reason we need to get this fixed is to get data off of the board. Most of all these soldered on SSD board repairs are all for data recovery now. So this board had liquid spill and then it stopped turning on. So as always, we need to plug in our USB-C amp meter and see what the board is taking. So just that brief visual inspection, I see some corrosion by the bottom CPU MOSFETs here. Now that is very concerning because if the CPU happens to get a voltage spike from one of these MOSFETs, it's going to die, or usually it's going to die in most cases. I'm going to go over that in the schematic in a little bit, but let's just go ahead and see what this board does. So I'm plugging in my USB-C amp meter. I'm going to show you guys what it's actually pulling. So let me switch over to my microscope here. Here's our amp meter. Where is it? Alright. 20 volts and 0.01. Now let me flip this around so you guys can see. So let's work a little bit of magic here and rotate this. And there we go, like magic. 20 volts, 0.01. So basically what this means is we have USB-C communication because we have 20 volts there. So we know we have USB-C communication, but the board's essentially not doing anything. That's why it's 0.01 milliamps. It's essentially using no power, so there's something going on in the power sequence that's stopping it from turning on. Can this be on a short on PP-Bus G3 hot? Absolutely. So as of right now, given the fact that one of the CPU MOSFETs is corroded, a short on PP-Bus G3 hot is going to be really on my high list of differential diagnosis. So let's go ahead and rule it out. I have my multimeter right here. We're going to just check voltage on PP-Bus since we have the board plugged in. If it's 0, then we're going to check for a short, but if we have normal voltage on PP-Bus, we know it's probably not shorted. So let's go ahead and check PP-Bus G3 hot on the fuses here, and it is 12.64 volts. So that means that there is no short to ground. Typically, when our CPU MOSFETs fail, we'll have a very low resistance to ground on PP-Bus G3 hot. Now that's not because PP-Bus G3 hot is necessarily shorted to ground, it's because PP-Bus G3 hot is shorted to CPU V-core, which has a very low resistance to ground. Let's go ahead and jump over to the schematic and let's explain that for a little bit. Okay, so here's our board view that's open. Let's have a look at this. So here's the MOSFET that was corroded right here, which is U1707. Now what we see here, we have a bunch of these lines right here, PPV, core, phase 2, whatever, okay? We have a few power rails here, PP5VSO, PP core SW2, switch 2 maybe, we don't know, and PP-Bus HS CPU. Now a lot of people forget this. They look at this and say, okay, that must not be PP-Bus because it says HS CPU. No, what this basically means, it is PP-Bus G3 hot, but it's going through a current sensing resistor and it's renamed to something else. So PP-Bus, anytime you see like PP-Bus, HS CPU, PP-Bus, HS, S5, computing, iSense, whatever, that all means the same thing. It is PP-Bus G3 hot. So this MOSFET is fed by PP-Bus G3 hot. That's going to be its source power. PP5VSO is going to be its auxiliary power. It might be powering a little brain function in the chip. And then we have our output, which is 1 volt for our CPU. You can see right here, it's going to go, it's going to power one of these inductors here, and it's going to power the CPU. So if we look at this inductor right here, not this one, where is it here? One of these guys. Here we go. Here we go. So here is our switch line, right? It's going to switch the inductor. Out of this inductor, there's going to be 1 volt or so. It's going to go through a resistor here for current sensing purposes, and then it's going to go to our CPU to power it. So how these guys fail, they don't typically fail in a way that they short to ground. What ends up happening is they actually short, they become a wire between PP-Bus HS CPU and this part of the chip right here. So it essentially just passes PP-Bus G3 hot through this, in through the coil, all right, and just gives the CPU a whole 12 volts. And what happens there, the CPU obviously gets fried. Now, you won't really get 12 volts there because if we do the math, the circuit that produces PP-Bus G3 hot cannot actually handle the power draw that 12 volts would take, sending it through a 2-3 ohm resistance to ground. But there would still be a brief moment where it might be like 6 volts or something like that, and that could do some serious damage to our CPU. So just to look at the schematic view right here, we will look at this on the schematic here. Let me drag it over my other monitor, and we see we have U1707. It's not quite a MOSFET. It's called a VRM. It's a voltage regulation module. It has a MOSFET in it. We just refer to them as CPU MOSFETs because that's basically what they do. But they're a little bit more complex than just a standard MOSFET. Okay, and it's going to be driven by an Intersil 95828 chip. Okay, and that's going to power our CPU. follow this line up, PPVCC SO CPU. Okay, that is the CPU SO power, voltage out 0.55 to 1.5 volts, depending on what the CPU requests, and ICC max 68 amps. Okay, that's how much power the CPU takes. So 68 amps is a whole lot of power. If we even look at my laptop right here, which is running this, we are probably sitting at 100 amps or so. So that's pretty crazy for a laptop chip that produces this. So if we look at this here, let's just look. Just because I know someone's gonna say, oh, 68 amps, that's wrong. No, that is correct. So let's find wattage here. So believe it or not, this is actually a laptop at 113 watts. Where is our amperage here? Somewhere here. Does it have it? It might not. Only wattage. Oh well. Well, just to point it out, that's what it is. So 68 amps, CPUs take a large amount of power. Now, when we're talking about this, for example, like what I was saying prior, the circuitry for PPBus G3 Hot is not going to be able to handle 68 amps, okay? Because it's going to most likely be even more than that if it's pulling it down. It's not going to be able to handle that, so we won't get a full 12 volts. We will get a transient spike in that. So we know that's not our problem right now because we have 12.64 volts on PPBus G3 Hot. So there's something else going on. So let's go ahead and just give an overview of the whole board and see what's going on, because we still know we have something going on. We don't quite know what. So in any liquid damage cases, I always tell people, don't overthink. Use your eyes before your brain. So let's go ahead and do that now. Let's have a look at our board under the microscope, and let's see if we can see anything. So I am just going to do a general inspection. I'm not ruling anything out at this time because we still could have a dead CPU on our hands. We still could have a MOSFET that's intermittently shorting to ground. I just want to establish what's going on. So I have some corrosion here. Now this looks pretty minor because it is not really touching any important chips. I have a speaker amplifier, maybe, but I don't really care. That corrosion right there isn't really touching any chips, so it doesn't really matter too much to me. Our backlight circuit, okay, that's not going to cause a no power issue. Carrying on, PP bus area. Oh, okay, there's a little bit of liquid near this guy. We'll figure out what that does in a minute. PCH area looks pretty clean. A little bit got by it, but nothing that would concern me. This area of the board looks pretty clean. Let's flip over to the other side. This area is really common to get hit. Looks fine. That's mainly for audio right there. BIOS area looks fine. Alright, a little bit right here. This is berkelium. That's an important chip, but it mainly handles touch bar function and T1 function, so maybe. CPU V-core. This is that ISL chip that drives the CPU MOSFETs. Here's our GPU controller right here. And, alright, so we have two contenders here. We have our CPU MOSFET here. Okay, that looks pretty bad. That's definitely could be part of our issue. But when we look at this, we can kind of tell that corrosion is mainly superficial. I mean, look at the copper there. It got hot. But is this our issue? Is this MOSFET shorted? No. It's not shorted because we have 12 volts on PP bus, and if this was shorted, it would be PP bus would be very low. So we know that's not the issue, but there could be an issue with this chip that's preventing the board from turning on. So what we're going to do, we just don't want this causing any problems when we turn it on. So we want to get rid of this corrosion. We're going to presume this chip is, for now, meaning it is going to do its job because it is not shorted, but we also don't want it to cause more issues. So I'm just going to clean around this real quick, just to clean the corrosion to prevent it from possibly causing any more damage when we do apply power to this. So that's clean right now, clean enough. We are going to move on. Possibly something got under our CPU. That's a definite possibility, but I'm most interested in this guy right here because this definitely got something under it. Look at that. So if we look at this at an angle, it's hard to see. There's definitely junk under that chip. Okay. Now let's look at this because this looks like a BGA chip. It looks kind of important. All right. So, and it definitely got liquid under there. So let's go back to our board view and let's try and figure out what exactly this guy does and what it's for. So let's open our board view again in our schematic and let's see what this does. Okay, so we have a BGA here. Okay, this one looks like something for graphics. DP means display port. All right, it's not that one, but this one. SMC, CPU GT vSense, SMC. I wonder if this is the SMC. Let's find out. Let's look at the board view. I mean the schematic now, and find out where this goes. All right, here's U5000. Let's look for a hint that can possibly tell us what this is. Alright, nothing here, no hints. Oh yeah, right here, look at this. SMC, right near the thing that says that we're supposed to be showing everybody how this works. But this is the SMC, and this is the System Management Controller. Now, the System Management Controller is responsible for a whole lot of stuff, and one of those things is enabling power rails down the line. So we have 20 volts, and it's not doing anything. It's just sitting there, 20 volts, not really turning on, not really doing anything. Now, our SMC is the orchestrator for a lot of stuff. All right, so if we have corrosion in our SMC, it can't really effectively communicate. And that is my guess to what is going on right now. So what I'm going to do is put a little flux around the chip and heat it up. Now, I don't necessarily reball just corroded chips off the bat. I've found just giving them a little reflow with flux and heat to be not inferior to reballing. I've pulled chips up that have had corrosion like that after a reflow, and there's really no traces of corrosion after ultrasonic cleaning, of course. So I usually don't reball these guys because usually the flux and the heat's enough to move all the junk out of there. Remember, the issue isn't our solder joints. We just need to clear the junk that's under that. The SMC isn't something that's really going to get damaged from water being under it because all the signals are all around 3.3 volts, right? So we're not really going to kill anything if we bridge 3.3 volts to 3.3 volts. What we're just going to do is cause communication issues and cause it not to work. So let's go ahead and give this a little flux and heat. I'm going to go back over to my microscope, and we're going to see if this works. We may end up having to replace it. We may not. We'll see. So I'm going to take careful consideration not to blow my hot air near anything that can possibly be damaged. Our RAM is shielded, so we don't have to worry about that. But I do worry about these connectors here, and I don't want the sticker to be melted, so I'm going to peel this off. It's just the sticker for the battery inductor. So I'm going to kind of blow my air this way, away from the connectors. And I'm going to use 430 Celsius at 120 liters per air. And I'm going to heat this chip until I see the flux boiling, and I could tap the chip and it moves. So we're just going to heat. I like to start a preheat above it to just kind of heat the board up so it doesn't get thermally shocked, and then I move in on it. You could kind of see in the flux all the junk that was under the chip kind of moving. Alright, I could tap it and it moves and we're done. Let's let this cool for a second and let's see if we have any change in our symptoms. Okay, the board is sufficiently cooled. Here's our SMC here. We still have to ultrasonically clean this. There's going to be a lot of flux here. We do have a little bit of junk right around here, but this isn't too much of a concern because after the ultrasonic cleaner, it's going to be more than fine. But let's go ahead and plug this in, and let's see if we have any change in our symptom set. Now, because this is the dual graphics variant, we should be getting a fairly high amp draw if it's working. So that's already a change there. 20 volts, 0.23, 0.1. That's where we're sticking before. 1.47 amps. Okay, that's more like it. So 1 point something amps is about right for this board to be booting. It's going to drop down a little bit once it posts. And one really quick way we could actually test these to see if the board is actually able to boot is measuring CPU vCore. Now on this particular board, on the pretty much all of the Skylake and KB Lake CPUs, if CPU vCore is 0.6 or 0.7 volts, that means the board is actually posted and is able to load an operating system. If it is 0.9 or high 0.8 volts, that usually means it's hanging on post, something's wrong. So let's find out the moment of truth, what we're actually getting here. So I have my multimeter right here, you guys can see it. I'm going to measure CPU vCore. Now I'm going to check the coil that has the really nasty looking MOSFET, because if that guy's working, I've tried to figure out, should I replace these MOSFETs? And the answer is if there's no pins that are seriously damaged and the MOSFET is actually working, then there's really no need to replace it. It's most likely not going to fail down the line. As you can see here, we have 0.648 volts and we are good to go. So what we are going to do is put this back in the enclosure, and we're going to see if it boots into an operating system. Now, let's talk about not replacing MOSFETs. Well, how do you know the MOSFET's going to last over time? The answer is stress testing. We use Prime 95 with small FFTs. It's very important on the small FFT part because small FFTs is going to put the CPU under a tremendous amount of stress. Run it for at least an hour or so, and if the MOSFET is going to fail, it is most likely going to fail during that test. And how the MOSFET is going to fail is usually not shorting to ground. How it's going to fail is voltage is going to be unstable and it's going to crash. So if you could run Prime 95 for an hour, 2 hours, whatever, with a MOSFET that is, had previous corrosion but is not terribly bad looking, the chances of that coming back or failing is pretty much nothing. Now, what does look kind of ugly around this MOSFET, which we are going to take care of, is the capacitor. And the reason why I recommend this and why I changed my recommendation is because these are really easy to screw up for people soldering. So it is a pretty easy chip to screw up soldering. And screwing up this chip as far as soldering goes can be really, really dangerous. So we look here, we have some corrosion. Now, under this MOSFET, okay, all of these pins, so we have a little break here, but all 3 of these pins here, all 4 of these pins are all on the same line. So if we have corrosion here, bridging between these, that's not really going to hurt anything because these are all the same. Same with here. Okay, so having corrosion here is really not going to affect anything. But if we had corrosion, let's say, on this side, okay, see we have a few different traces, right? If we had corrosion on this side, it was all nasty, spilling over to this side, that would be bad and the chances of damaging the chip are higher. But if it's just like right here, kind of minor, we really don't need to worry about replacing this chip. Anyway, what I'm going to do is put some flux around here, and we're going to get rid of this capacitor because that is concerning to me, and those capacitors can short to ground. Let's get some flux in here. And now another thing, I'm going to use a really excessive amount of flux here because I want that flux to kind of get under that chip and dissolve anything that may be under there. So one of the nice things about Amtech NC559 or NC560 is it is actually formulated for oxidation and heavily oxidized boards. So there is chemicals in the flux that actually chemically dissolve the corrosion there. So it kind of breaks it down and turns it into something that is no longer corrosion. So we're heating, and notice I'm heating away from the CPU. So I see a lot of people heat towards the CPU, and that is very bad. Don't do that. So leave the heatsink on as well. This guy is off. I'm going to keep heating the MOSFET until I could see it kind of move. Like that. Same with this guy. Okay, it's moved. All the solder joints under there are patent. They're not corroded or anything because if it was, it would not move. Now this little bit right here that we see, that is going to be purely cosmetic on the edge, and this pad actually extends deep under this chip. And I'll actually show you on a donor board in a second here. But we're just going to kind of scrape. And then right here, we just want to take away that layer of oxidation. Just like that, a little bit of flux. Now I have my iron. Get some fresh solder in here. Take care of this bridge. Now this is a really high thermal mass area. As you could tell, the traces are absolutely huge. So you can get bridges like that. That's okay. It's common, especially in this area. Now let's go ahead and grab our replacement capacitor off a donor. Any of those solder joints that look ugly are going to flow into place nicely once we apply hot air like we're doing now. just like that. And we're done. Let's go ahead and grab the enclosure and let's see if this boots into an operating system. Alright, let's plug our charger in. Charger is plugged in. One of the key things that's going to tell me if this is turning on is if I feel the trackpad, the actuator power up, and I could click the trackpad. We're at 20 volts, 0.1, 1 amp. The actuator is on, and I have a two spinning fans. That is a chime. And that is an Apple logo. Let's see if this actually boots into the operating system. Because remember, our CPU could have got a voltage spike that we don't know about. Let's see. I'm going to try and turn it so you guys can't see the customer's info, the name, because I don't know what's going to pop up on the screen. It's probably booting into recovery mode, as always. It's a common thing on this channel. Come on. Battery's unplugged too. The battery BMS board has a little bit of corrosion, so left it unplugged for now until I get data. And that just switched display modes. I have keyboard backlight. I have touch bar. Come on. There we go. This is booted into an operating system. So this appears to be fixed. And that's it for today. So another one fixed. Another one, somebody else's data recovered. And today's a good day. So thank you for watching. And I hope this video helps you some way solve your problem.